Welcome to new video on wind loads based on AS/NZS 1170.2 structural design actions. Let's explore the complete procedure for calculating design wind loads step by step. AS/NZS 1170.2 provides the requirements for calculating wind pressures and wind forces. It ensures buildings and other eligible structures are safely designed for both ultimate and serviceability limit states. Wind load calculations begin by determining the site wind speed using the standard equation. This value is then converted into the design wind speed, which forms the basis for all subsequent wind pressure and structural design calculations. The design wind pressure is calculated using the AS/NZS 1170.2 governing equation. It is then converted into the design wind actions by applying the calculated pressure over the effective structural area. The first step is collecting the basic structure details, including the site location, building height, plan dimensions, roof type, and importance level. These parameters form the foundation for accurate wind speed and wind load calculations. Identify the wind region based on the project location using the AS/NZS 1170.2 wind maps. Selecting the correct wind region is essential because it determines the design wind speed used in the calculations. After selecting the wind region, obtain the regional wind speed, or VR, from Table 3.1. The value depends on the wind region and the annual probability of exceedance, providing the basis for all further wind load calculations. The wind direction multiplier accounts for the likelihood of wind coming from different directions. Its value is selected from AS/NZS 1170.2 tables based on the wind region and design requirements. The terrain height multiplier depends on the terrain category and building height. It accounts for the effective ground roughness on wind speed at the structure. Table 4.1 provides the terrain height multiplier values for different terrain categories and heights. These values are directly used to determine MZ, CAT for wind speed calculations. The shielding multiplier, MS, considers the protection provided by nearby buildings or structures. It reduces wind effects only when the shielding conditions specified in the standard are satisfied. The topographic multiplier, MT, considers the effects of surrounding terrain on wind speed. It is determined using the hill multiplier, MH, and the lee multiplier, MLE, as specified in AS/NZS 1170.2. The hill multiplier accounts for the effect of hills on wind speed. For flat terrain, MH is 1.0, while steeper hills increase MH and the resulting design wind load. The lee multiplier, MLE, considers the wind reduction effect in lee zones behind hills. It is evaluated only for structures in lee zones, otherwise, MLE is taken as 1.0. The lee multiplier, MLE, considers the wind reduction effect in lee zones behind hills. It is evaluated only for structures in lee zones, otherwise, MLE is taken as 1.0. The aerodynamic shape factor, or CSHP, determines how wind pressure acts on different building surfaces. Positive values indicate pressure toward the surface, while negative values represent suction away from the surface. The internal pressure coefficient, CPI, accounts for wind pressure inside the building caused by openings or air leakage. The appropriate value is selected based on the building's opening conditions. The external pressure coefficient, CP, represents wind pressure acting on the outside of the building. It depends on the building geometry, roof pitch, and wind direction. The area reduction factor adjusts wind pressure based on the effective loaded area, while the action combination factor considers the combined effect of wind acting on multiple building surfaces. The local pressure factor accounts for higher wind pressures near roof edges and corners. The permeable cladding reduction factor is applied when the building cladding allows air to pass through. The area reduction factor adjusts wind pressure based on the effective loaded area, while the action combination factor considers the combined effect of wind acting on multiple building surfaces. This table shows the action combination factors, K and KCI, used in wind pressure design. These factors combine external and internal wind pressures for different structural surfaces to determine the critical design load. The local pressure factor, KL, is applied to account for higher wind pressures near roof edges, corners, and other critical regions. For permeable cladding systems, the reduction factor Kp is used to modify the design pressure based on airflow through the cladding. The dynamic response factor considers the effects of wind gusts, turbulence, and structural vibration. For low-rise rigid buildings, it is generally taken as 1, while taller structures require detailed calculations. For tall buildings and towers, the dynamic cross-wind response is also considered. The coefficient C/Yn is calculated using this equation to account for wind-induced vibrations and ensure a safe structural design. After determining all pressure coefficients, the wind loads are combined according to the code requirements to identify the most critical loading condition for structural design. This presentation is based on the Australian standards AS 1170.2 for wind actions and AS 1170.0 for general structural design principles, which provide the requirements for wind load calculations.